Okay, good afternoon, everybody. How did that unit test go? Yeah? Were you surprised by anything that you saw on the unit test? Did it match that learning objectives sheet? Did anybody look at that learning objective sheet while the test was open and like check things off to say like, oh yeah, he did say we would do this?
I had it open, but I didn't do that.
I tried to actually build that learning objectives sheet off of the question banks that you get questions from on the unit test. So they are meant to be directly paired. I'm trying to tell you what I'm going to assess you on. And obviously, like, I can give you a list of words, but sometimes it feels really different when you're actually seeing the questions at play. Okay, well, I'm glad to hear it. You guys did really well. Actually, why don't I try to give you the breakdown of how things went on that unit test? Some averages. Not projecting, right? Great. Average on part A and part B. What do you guys want to take a stab and guess? Give a letter grade, give a percentage. What do you think the average was on the multiple choice part A? 98. Okay, anybody else? 98 is pretty high. Well, it was the same letter grade. It wasn't A, but it was a 93% average. Pretty good. I think I told you guys. Oh no, maybe I didn't tell you this. I usually tell my labs, but maybe like 8 times out of 10, the only reason somebody doesn't get a 10 out of 10 on that quiz is because they don't take their second attempt. And sometimes that happens because they start it at 11 p.m. and they don't have time to take a second attempt. Sorry. What about part B? What do you think the average was? Higher or lower than 93?
Well, I'm guessing just based off of the fact that it's 5 points,
Higher stakes, right? And you only get one shot. So if you make any mistakes, that time you're kind of done for. For example, one student got 5 out of 10 on their first attempt of part A, and they got 10 out of 10 on the second attempt. Great. Shows me mastery of the concepts. They figured out where their weak spots were, they studied it, they did better the second time around. The average on part B was an 84. Not bad, honestly. That's still a B average. And in the past, my midterms have gotten B or higher averages sometimes. And so I would say this is setting you guys up well for good trajectory into the unit, into the midterm. All right, cool. That was fun. Well, I bet none of you saw this coming, but I uploaded the learning objectives for Unit 2. Now, if you remember, Unit 1 was 2 sections, and they each had 5 or so objectives underneath it. Unit 2 is 3 sections, and it might surprise you, but they each have 2 or 3 things underneath them. That means that, there are some things that I need to actually add to section 5, so that is why it looks so small. And it might feel like as we go through it, I need to update some of these. So we will make those modifications. One of them to section 5 for sure. I'll make sure that's updated before we get to section 5. So please take advantage of this. If you felt like it was useful for the first unit test, I need to, I copy and pasted the document. So I need to go through and change that at the top to say Unit 2 learning objectives. All right. This section predominantly focuses on alkane structures. But to understand what alkanes are, we need to understand what all functional groups are. Now, if you've had a friend that's taken organic chemistry in the past, they've probably told you something like, make sure you memorize your functional groups. Make flashcards of all of those. Do you guys have an idea from your readings, from your experience, of what functional groups are? How would you define them? Yeah. Sorry, I thought you were raising your hand to answer me. No.
Are they molecules that really like to attach themselves to other things?
Functional groups, molecules that like to attach themselves to other things. No. But I'm curious, what makes you think that?
Just looking at some of these, the functional groups, it's generally R to like OH or R to sulfur to R, which just would lead most to attach to other things.
Ah, what is R? Do you know?
Um,
Because I think you're saying here's this group of atoms and they're attached to other things. But is that group of atoms a molecule that likes to attach to other things? Or is R included in that molecule?
R would be
R's included. Anybody else want to give a shot at functional groups? Thank you for sharing.
I like groups of atoms that have specific properties and they're like as a group.
Groups of atoms
A lot of groups.
with specific properties. Why not add groups of properties? With specific properties. What was the last thing you said?
Like when they're together, like as a group.
As a group, they have specific properties. What do you guys think? Do you agree with what Elliot said? Functional groups can be thought of as groups of atoms that have specific properties because they're together. Did you do the reading?
Maybe like a specific function as a group.
A function does something. Well, that would, I like that. Well, and sometimes a property is a function, right? A function, I think, is a bit of a subjective term. Do you want it to do it, or is it going to happen and you need to try to avoid doing it? You want to inhibit its function? What do you guys think? Is Elliot on to something, or is he off track? Do you want to add anything to that, Bella?
I think with
Specific
specific bonding characteristics.
bonding. So not just the elements themselves or the atoms, but the way they're bonded also matters. Yeah? Okay. Functional groups. Can we use groups in the definition of groups? We could say sets. Sets of atoms. In specific bonding patterns. That share properties. Typically, chemical properties. They react in similar ways. Not necessarily physical properties, but, you know, it can sometimes be physical properties. How many functional groups is a molecule allowed to have? One? One functional group per molecule? Two? I mean, it's got to be countable, right? Like 10? Why does a molecule need to be limited? DNA is one molecule. Well, each strand is one molecule. But DNA actually only contains about 10 functional groups. There's not that many unique bonding patterns within DNA. Here are the three ways that I like to categorize functional groups. I wouldn't necessarily say that textbooks report it this way, but this is a good way of thinking about it. First, we have our hydrocarbon groups. The only sets of atoms that you have are carbons and hydrogens. And then the way that they bond distinguishes them from each other. We have carbon-carbon single bonds, carbon-carbon double bonds, and carbon-carbon triple bonds. You'll notice I didn't actually put any hydrogens in here, right? That's because hydrogen would just be satisfying the rest of those bonds to those carbons. And if we wanted to say that these carbons can be bonded to other things, we can actually abbreviate the rest of the molecule by just putting R in here. R is meant to say rest of the molecule. You guys okay with that? We could have picked anything really, but X already means halogen. Y is typically a variable that we put into equations when we're not trying to say something specific, but something generic. And R has become the standard for the rest of the molecule. In fact, we can abbreviate R in different ways. We can say R1 and R2 to distinguish different R groups, although sometimes that subscript makes it look like I've got R and two of them. So we can also have things like R prime, R double prime, just to say generic things that aren't necessarily the same generic thing. What's the smallest thing R could be? Another carbon? Why don't you guys talk in your groups? Discuss what you think the smallest thing that R could be abbreviating could be. What do you think? Is another carbon the smallest thing you could put? Wouldn't that carbon need more bonds to it as well? And wouldn't that kind of extend the rest of the structure? What's the smallest thing it could be? A hydrogen? Or maybe even a halogen, because halogens often only have one bond, like hydrogen. So oftentimes, you'll see organic structures that have an R group coming off, and people are doing research on how the nature of that R group changes the properties of the chemical. And they'll say when R equals H, these are some of the effects. When R equals Br, these are some of the effects. When R equals CH3, these are some of the effects. When R equals however big, however long, however small you want it to be. And these are the effects. Okay, those are the base hydrocarbon functional groups. You'll notice there's one that I left off, and that is the benzene ring, the aromatic ring. These three all have a very similar naming pattern. They all begin with ALK. That prefix ALK is meant to remind you of hydrocarbon. We'll be using ALK as a prefix for a number of different things. ALK-ane is your single bonds. Alkane. ALK-ene, alkene, is a carbon-carbon double bond. And ALK-ine. Do you know what? I struggled with remembering how to say that, so I'm going to make you all say it with me today. I'm going to say it once, and then you're going to repeat it with me, okay? That is alkyne. 1, 2, 3, alkyne. because a lot of people pronounce alkene and alkyne the same, because in English, that Y doesn't make a specific sound. So it looks like it could be pronounced alkene as well. All right. The last hydrocarbon chain is a 6-membered ring with alternating double bonds. Do you see any confusion between some of the sets of atoms and specific bonding patterns that the aromatic ring has with one of the other hydrocarbons? What's an overlap they have? Alkenes have carbon-carbon double bonds, and the aromatic ring has carbon-carbon double bonds. So are we saying that aromatic rings are a functional group that contain alkenes, a second functional group? Is that what you would presume? That 6-membered ring is both an aromatic ring with alkenes inside of it? Then how would we say that they are different? We'd have to know that they have different chemical properties. Alkenes do not react the same as aromatic rings. It may look like there are double bonds in that 6-membered ring, but guess what? MO theory doesn't think that there are double bonds in that aromatic ring. MO theory says there is a pi bond that goes all the way around the ring. Not a pi bond between sets of atoms, but one pi bond across all 6 atoms. Do you know what I'm saying? A molecular pi orbital. And then there are 2 other pi orbitals that have some nodes within them that break up some of the pi bonding character kind of in that way. Aromatic rings are not alkenes. They do not have alkenes in them. They have different properties. And so here's how I'm going to say that. This is not an alkene. It's not cyclohexatriene. It's not a 6-membered ring with 3 alkene bonds. It is its own thing. My OChem 2 class just had their unit test this weekend as well. And on one of the compounds, I have an aromatic ring, and they have to answer what functional groups are in here. One of the options is alkene. And the correct answer has combinations of the options. But of course, alkene is not one of the correct answers. It trips them up, and I need it to trip them up, to remind them these are different functional groups. They have different properties. All right. The other classes are the carbonyl families and the heteroatom families. So carbonyl is a CO double bond. That is a set of atoms with a particular bonding pattern. So it feels like carbonyl is a functional group. But notice I have not described what is bonded to the carbon. It's too limited. Carbonyl is not a functional group. It's a class of functional groups. Depending on what is bonded to that carbon, the functional groups change. So we're going to look at some functional groups and then some heteroatoms. By the way, this document that I handed out, you can find it on the homepage. I know a number of you have already utilized it. So I'm going to pull this up and show you guys. Here are the carbonyl groups on the left-hand side. This is actually a selection of them. I think that you can say that there are more. And they depend on very specific things, like the aldehyde always has one hydrogen bonded to the carbon of the carbonyl. That is what it must have in order to be an aldehyde. I remembered when I was in college, I remembered what the aldehyde was because it always hides over here at the end of the molecule. Silly. That's okay. You need to come up with silly things. A ketone, well, the ketone to me actually kind of looked like a key. So that's how I remembered it. Doesn't the aldehyde kind of look like a key? Yeah, but it's okay. I had another way for remembering the aldehyde. The carboxylic acid, well, this actually has an OH group directly attached, as opposed to an NR group, as opposed to an H, as opposed to two carbon groups. Notice that on my table I explicitly state R can't be hydrogen here. It has to be a carbon group. Well, this OH group, it actually makes me think of one of the heteroatom functional groups. And that's this alcohol family right here. So I looked at the alcohol and then said if you have what looks like an alcohol with a carbonyl, then it's kind of like the alcohol version of the ketone. Okay, so just bear with me. This is how I remembered it in college, and I encourage you to come up with your own dumb ways of remembering it if this doesn't work. But I said, well, if this is a carboxylic acid, then it looks like the key to the alcohol that Dad keeps in his car box. What's a car box? I don't know. It doesn't matter. It's just a silly way of connecting things so that you can figure it out later, right? Honestly, it's a terrible thing. But guess what? Carboxylic acids, do they have an alcohol? Is a carboxylic acid one group of atoms with specific properties that also contains an alcohol? What do you think? How would you determine it? You'd have to test their chemical properties, right? And the reason I'm taking up the space on the board is because they're not the same. There is no alcohol in a carboxylic acid. And I tell my OChem 2 students again to remind them, you don't look at a carboxylic acid and say, well, when the alcohol does such and such. No, there is no alcohol in the carboxylic acid. When the OH group, yes, they both have OH groups, but those OH groups have different properties. One of those properties is resonance in the conjugate base. Alcohols don't have resonance in the conjugate base. Carboxylic acids do. That changes their acidity by about 10 orders of magnitude, 10 to the 10. That resonance makes carboxylic acids 10 billion times more acidic than alcohols. Cool? There's another one that's very similar. I'm going to put it down here because I kind of ran out of space. That's if we have the amide family. That's a carbonyl that's bonded to a nitrogen group. And I do want to say, I say R2, and a lot of students think that means R has to be a carbon chain, but it could be H2, it could be HR, it could be NR2. There's a lot of variations here. And these are not the same as their heteroatom relative, the amine. This is the amide, and the amine is actually up there a little bit. I'm just going to scroll up, which is going to ruin everything else. The amine has this nitrogen group bonded to a carbon chain. But you'll notice we actually differentiate. If that nitrogen is only bonded to one carbon group, it's primary. If it's bonded to two carbon groups, it's secondary. If it's bonded to 3 carbon groups, it's tertiary. If it's bonded to 4 carbon groups, it's quaternary, but it's no longer amine. kind of like how ammonia stops being ammonia once it's NH4, it becomes ammonium. This is an ammonium ion. It becomes tetramethyl ammonium chloride. So, similarities in structures with big, big differences, okay? I want to give you guys an activity with these, kind of a two-part activity. In pairs, I'm going to break you into pairs. You don't get lucky today. In pairs, I want you to pick a functional group. Find a compound with it. I'd like for it to be in your life somehow. Maybe it's a medication that you've used, or medication you've heard of. Maybe it's part of a material that you have in your house. Trust me, you'll find something that connects to your life. And then I want you to look at this list that I've handed out. And I want you to see if there are any other molecules on the list that also have your functional group. And if there aren't, I want you to prove how you know. What did you look for that proved that there was no duplicate of that functional group in one of the given example structures? Make sense? No? And then the last thing you're actually going to do is you're going to come up and report on the board. You're going to give me the structure, the name, and if it repeats on this list, if it's indicated in any other example. Is that okay? Anything I can clear up on that? Makes sense. I lost you guys today. All right, well, I'm going to get you moving. So if you would please arrange yourselves on the back wall from tallest to shortest. Oh. I ran out. Actually, I can make a couple extras. Anybody not draw on theirs yet? Okay, I might draw yours in a little bit, Indigo, then. I'll break you guys up first. You guys can scoot more this way. Maybe Will, can you scoot down more? You got more space this way. Keep coming. File in. Scoot down. Yvonne, you're taller. Yeah, sorry. It's okay. You're not graded on this part of the activity. But I think you're Yvonne. You're gonna go before New, and Mel, you're gonna go before D. All right. These are your groups. I'm going to pair you from opposing height. So this is actually crazy. Will and Andy, you guys are together. They sit right next to each other, which is weird. Elliot and Natalie, nailed it. Hayden and Indigo. Peter and Belen. Aiden and D. Yoon and Mel. You're just in time, Jenny. Stay right there. Elise and Jenny. You guys are a pair. Kiara and New, Nicole and Yvonne, Jackie and Sarah, and my lucky two, Alyssa and Kira. Ooh, that was so hard. All right, can I borrow this? Copy.
Oh, really? Okay, right on. Do you guys ever use lighting canes? Yeah. That's good. I work in dermatology, so like, we use lighting cane a lot.
I didn't mean to do that. I totally forgot. I know.
Use lighting canes. That's like the compound that we're looking at throughout the semester.
Sorry. I thought you were like waiting to ask me something.
Oh, yeah, I guess.
You're gonna draw it up here on the board. Whichever one is easiest. I think we'll find online is easier.
Probably.
Oh, you've got like a badge? Yeah, because then you can do CH2 8. For instance, oh, sorry. Yeah. Yep.
I've used all three of these.
Oh, you all started, didn't you? I didn't have you guys pick functional groups. I was like, yeah, but what if you duplicate? Ah, shoot. All right, hang on. Maybe we got lucky, but I'm gonna go in reverse order, and if somebody else chooses your functional group before you, sorry. All right, so I think reverse order we had Alyssa and Kira first. What's your pick? Ether. All right, if you had ether, you're out. Who did I have next? Kiara and New? Ketone. Who was next? Jackie and Sarah. What do you have? Alkane. Who is next? Then I think I'll say Aiden and D. What do you guys pick?
Amides.
Amide. All right. Indigo and Hayden? Amin?
Yeah.
All right. Nicole and Yvonne? Carboxylic acid is off. Malonyl. Sorry? Oh, yeah. That is a tough one. It's pronounced imine. Amine, imine. But imine looks right. Peter and Belen. Alcohol. Jenny and Elise.
Yeah. I mean,
Aromatic ring. Elliot and Alyssa. Did I already have you go? Natalie, I'm sorry. The alkyl halide. All right. And now I think I'm on my last group, which is. All right. Sulfite. Did I miss anybody? All right. It worked out.
When you say repeats, it just means it doesn't occur multiple times with one compound.
So does it repeat anywhere on this list?
Oh, okay.
So like you guys picked what? Amine.
Yeah.
And I gave you. Did you do this?
No, we did.
Yeah. Oh, good. Yeah. So then look for any other compound on here.
Okay.
You know what I mean? On this list that I gave you, you picked what functional group?
Ketone.
yeah.
So look to see if any of the other compounds also have a ketone.
Oh, okay. So it wasn't on what we found that we were trying to find if it repeats.
That's right.
We were trying to find it on the paper.
That's right.
Okay.
I have no idea.
I know.
Just in case.
Do you like cabbage? That might be the best line. The best line to come out of my chemistry class. Belen, isn't that your compound?
Yeah. He uses sunscreen.
Okay, fine.
Do you not use sunscreen?
No, never. No, I do. I have a bald head, Belen. I have
See,
to.
everyone uses it.
I have to protect it somehow. And I don't know how to access zinc oxide. Oh wait. Meaning on this table. Is there any right? You guys does any of these other compounds also have? I don't know what I don't know. Anywhere else? You have not Your Caesar. No. Oh, we know. Oh, okay. never noticed that.
We're just right above them.
Oh, okay. I was like,
Yeah.
Yeah, I was gonna say, you go pretty high.
do you want to write or do you want me to write?
You can write it if you want.
So,
And I originally got computer science. It's a lot of classes.
what it's
Yeah. Or like a Dino. Or like
We do?
I mean, I'm
Alright, you
just.
guys understand what I meant?
So I think it's like.
No. Like, is there any other example in this?
Now, schools do that also have.
It seriously does. Okay. And then it repeats at start.
There is another example with narrative. Where else?
And
That's what I'm saying. Yeah.
I honestly enjoy Alkanes more than work at one
I feel like
right. This is guy.
AI.
I think part of it too is UAs is locked down my brain.
What do you find?
I'm trying to find work around classes like that. That's kind of one. Because I took it from COVID.
we need that. We need that. A whole point. Okay. So the name. So first I think we can put like cardinal.
Should we put can you write an email or just
I will do header ad.
right?
You guys looking for yours or you're good? Okay.
Do we have to rate this?
I did already. Okay, thank you. Great job too. That is a tough structure. Yeah. Yeah, way to go. I mean, you could have gone a lot easier.
I know, I was like, we're just gonna go for it.
You know aspirin? Aspirin's got like 10 carbons and carboxylic acid. But this is great. I love it. That's right. No, go big instead of going home.
It looks good.
You get to stay. I learned so much from this activity. I love it. They did it. They actually asked me explicitly. And I'm glad they did. I actually feel like I can get more information out of it written that way than I could if it was. Yeah, I agree. That ether could have been abbreviated probably. It's great. Well, we were just saying underneath yours is the protein structure. It's abbreviated. You guys probably could have gotten away with saying you got 1, 2, 3, 4, 5, 6 CH2 groups on either side. But it does look, it's just in time for spooky season. Yeah.
What is sulfide? Yeah, that's a spark.
Oh, this is a sulfide.
Oh, it's getting confusing. But
So yeah, I'm
No,
taking
this is good. I actually don't mind having small and large animals.
okay, I just
Organic chemistry has all.
I only know that. I only ever heard it's called just like
And where do you find that?
and then they also involve something more engineering.
so
I don't know. Maybe. Yeah. I think I had like a purple soup one time. Cabbage soup. Christmas in London, you know. All right, thank you guys. I hope that this exercise helps you feel a little bit more connected to the functional groups and gives you a little bit more awareness of just how complex organic molecules are and how many functional groups they can have. So now I do want to kind of go through them with you. So let's start up here and look at Alyssa and Kira's compound. You picked dicaprylyl ether, which is a terrible name. This part, not your fault, sorry. This part, caprylyl, is not systematic, it's common. It probably comes from something. And so if you don't know what it means, it's meaningless. But we were talking earlier about how this is 1, 2, 3, 4, 5, 6, 7, 8 carbons long on either side. So we could just call it dioctyl ether. We're going to talk more later today about how to use nomenclature in order to communicate about compounds. So you picked this because it's in?
Moisturizer.
Right. It's your moisturizer. Now, on that list of compounds, did you find ether repeat anywhere else?
Not after we looked again.
Good. So you actually wrote down here that it repeats in the ester and the acid anhydride. And what you noticed is that there's a carbon, oxygen, carbon, carbon, oxygen, carbon unit. Just like in the ether, carbon, oxygen, carbon. In fact, the way that I like to remember ethers is that it is oxygen with carbon on ether side. That is good. I see students that have shirts that say organic chemistry. Either you get it or you don't. It's good. It's a good way to remember it. And there is an oxygen with carbon on either side, but notice something about these carbons. Those are carbonyls. And that changes the chemistry around that central oxygen. So they have a different set of atoms, a different minimum set of atoms needed to describe it. Ether has just carbon, oxygen, carbon, but ester needs to have a carbonyl, and anhydride needs to have 2 carbonyls. So I know we said that it repeats up here, but the ether actually doesn't repeat anywhere on the structure. So that's similar to what I gave over here, right? Benzene is not an alkene. Carboxylic acid is not an alcohol. Amide is not an amine. And the ester and anhydride are not ethers. Great. All right, let's move on. Why do I always just put initials? That's terrible. Jackie and Sarah. What did you pick?
Vaseline.
Your functional group was alkane, and you went with Vaseline. Great. Petroleum jelly. Notice that the only thing in this compound are carbon-carbon sigma bonds and carbon-hydrogen bonds. There are no pi bonds. There are no heteroatoms. And to be fair, alkane is considered the base functional group to such an extent that if there is any other functional group, alkane is often ignored. It's not even said to be there. So if we look at somebody else's, well, it's actually, we've got some pretty complex structures up here. All right, the ether is probably the best. I've got this really long series of just alkane. before I actually get to the ether unit. But if you talked about this moisturizer, you wouldn't say it has alkane functionality. Oftentimes you'd hear people say it has an ether functionality. So the only time we really highlight alkanes is when it's simply alkane. This is great. Now, did you find that it was anywhere else on the structure list? And I think because of that same argument I just said, even if you look at something like the nitrile example, 2-cyanopentane, which is kind of in the middle right, there's a series of just carbon-carbon sigma bonds, but because there's something else in there, it often won't be labeled. Good work. All right. I have to guess. K and N, Kiara and Nu. Thank you. You guys had ketone. What compound did you choose and why?
Acetone. We were gonna pick apples, but we couldn't find the structure.
Apple?
Yeah, like fructose apparently has it.
Ah.
What?
Yeah, linear fructose, but not cyclic fructose. And I think by the time you eat it, it's usually cyclic. I could be wrong on that.
That's probably why we couldn't find
Okay.
it. But
If you search chemical in apple, you'll probably find about 100 things, to be fair. Oh, yeah, I mean, apples are ripe, no pun intended, with organic compounds. Okay, so you went with acetone because?
it was easy after.
What-
Never find something else.
What do you use it in? What do you use it for, I mean?
Nail polish.
Yeah,
Remove.
acetone is nail polish remover. Those of you that have used nail polish remover before, when you get into the organic lab, it's just going to smell like a beauty salon. And did you find that there were any other ketones on this list? There are a lot of other carbonyls, but you had asked me a really good clarifying question. On that list, I say R cannot equal H. So then it kind of implies, well, as long as there's something other than H connected, it can be called a ketone. But if it's also an oxygen on either side, then it's either an anhydride, an ester, or a carboxylic acid. And if there's a nitrogen, then it's an amide. So really, it has to be 2 carbon groups in order to be a ketone. Otherwise, if there's any other atom connected to that carbonyl carbon, it's not a ketone. Okay, good work. Let's see, was this Aiden and D? Great. You guys had amide, what'd you pick?
We picked carbocaine.
Carbocane.
Yeah.
I've not heard of carbocane.
It's an anesthetic.
Yeah, it sounds like it's part of the cocaine family.
You would hope.
Okay, no, sorry. It is part of the cocaine family. So are benzocaine and lidocaine and narcane? Marcaine. I feel like there's another. Novocaine. And you call it what?
Carbocaine.
Carbocaine.
Yeah.
Cocaine is known for its anesthetic properties. The problem is when you use it as an anesthetic, it gets patients incredibly addicted. So researchers tried to model the structure of cocaine to minimize the addictive effect, but maximize the anesthetic property. And that's why you have this family of canes. So it was not a joke that it's part of the cocaine family. But this is great. Actually, part of the cocaine structure, family structure, is having this amine on one side. And you'll notice this is a tertiary amine. It's a nitrogen that has 3 carbon groups bonded to it. But this group is actually the amide, where the carbonyl is bonded to a nitrogen. Now, when you looked at that list, did you find amides on any other structure other than glycinyl alanine? I made this, but I can't read it. Did you find amide anywhere else in the list?
No, I think. Sorry, I was confused. I thought that it was like what other ones are in the structure, so that's what we put heteroatom on there. So
Oh,
like,
good.
There's an amine in there.
So on the amide example, glycinyl alanine, there's also an amine But there's also a carboxylic acid in that example, which for those of you that know about biology, a peptide will always have an amine somewhere, a carboxylic acid on the other end, and at least one amide linking them together. Okay, good work. This is Yvonne. No, must not be Yvonne. Oh, Indigo and Hayden. I was like, Elliot? No way. Okay. You guys had amine, not to be confused with amide. What'd you pick?
L-theanine, it's amino acid and tea and Celsius and a bunch of energy drinks that has a calming effect.
Do we need it in our body for building proteins? Do you know?
Amine?
This L-theanine.
We do not.
Oh, okay. So it has like a neurotransmitic effect, but we don't actually use it for building proteins. Interesting. Very cool. And you'll notice that the amine here is actually in this part, not in the amide. And this is also an amino acid similar to the, or it's a peptide, excuse me. Kind of. Similar, it's similar to the amide example that I have on here. Hayden and Indigo, did you guys find a repeat of amines anywhere on this list? Actually, I think on the amide example, there is an amine because it's got that NH2 group that sticks off on the left-hand side. That's an R bonded to an NH2, and it's not part of a carbonyl. Do you agree?
Yep.
Yeah, a primary amine, whereas yours is also a primary amine. And the example that Aiden and Dee had was actually a tertiary amine. It's a nitrogen group. It just depends on how many carbons are bonded to it. Okay, cool. Let's go on. Nicole and Indigo. You guys had carboxylic acid, so what did you pick and why?
We chose meropenem because it's an antibiotic that I work with a lot.
Nice. Now that is an impressive structure to draw. Was there anything you had to repeat, like erase and try and redraw it?
No, just went for it.
Way to go. Getting these 4-membered and 5-membered rings that aren't even connected, they're connected by like a linear chain, it's really hard to do. I don't know if you guys have ever looked up the structure of oxytocin, the love drug, but it's actually this huge macrocyclic structure, and I attempted to draw it once in college. And you have to like really plan for where everything is going to come back and connect. This is impressive. Great job. You said it's what? It's a
It's an antibiotic.
antibiotic. Have you used it before?
Not myself.
Have you given it, administered it,
I've compounded it.
compounded it? What does that mean? Tell me more.
Well, it's not, I guess. It's basically where I add NS to a vial and I draw it up and shoot it in a 100 NS bag, and then the nurses administer it.
Oh, sure. So you've made it ready for administration. Cool. Very cool. All right, and you guys said that carboxylic acid, which is right here, not to be confused with the amide or the ketone that are in this structure. But you said that the carboxylic acid does not repeat on this list?
I thought it was referring to does it repeat?
That's okay. I know. I didn't explain it well. But now let's take a look and see if there are carboxylic acids anywhere else other than 2-aminoethanoic acid, also called glycine. Do you see carboxylic acid anywhere else on this list? The amide example also has that carboxylic acid in it. Cool. Great job. Can't have that many Y students. Mel and Yoon, you guys had imine. What compound did you pick and why?
Caffeine, because it's one of the only things keeping me afloat in this hellscape right now. I joke. But yeah, we chose caffeine.
Good. Now the imine is an interesting functional group. It's a carbon double bonded to a nitrogen, which gives it different chemical properties than a carbon single bonded to a nitrogen. Caffeine also has an ene amine. That is an amine bonded to an alkene. I guess, yeah, here's the alkene, carbon-carbon double bond, bonded to an amine, just carbon-nitrogen single bonds, a tertiary amine. That makes it a tertiary enamine. And that amine is also connected again, kind of in a similar enamine fashion to the imine, not to be confused with the amide or the diamide that are in this structure. A lot of nitrogens. I don't know if you guys know this, but bioorganic chemistry needs a lot of nitrogen. We're not actually going to look at nitrogen a ton this semester because its ability to be a base and a nucleophile makes it a lot more challenging to work with and understand. And so you see nitrogen more at the end of OChem 2 than you do in any of OChem 1. Okay, good work. Oh, did you see imines anywhere else on that list other than the example? No. Okay, Peter and Belen, you guys picked alcohol. What'd you pick and why?
Well, I chose one to hexyl because it's a moisturizing agent. It's like a moisturizer, sunscreen, you name it.
Do you know if it has a moisturizing effect or a sunscreening effect?
It has a moisturizing effect. It is a sunscreen, but it isn't like the sunscreen effect. It just moisturizes your face or like your body. But it's a moisturizer because the moisturizer's main job is to moisturize.
Good. You guys will find if you look at ingredients for sunscreens that they often contain zinc oxide, which is able to absorb UV light through its metal that's in there. Or they contain aromatic compounds, and the aromatic compounds actually absorb UV light through its pi bonds. So compounds that don't have pi bonds can pretty quickly be ruled out as not being part of the sunscreening effect. Great. And this is actually a diol. This compound has not just one alcohol, but two. Great job. Yeah, it's just really gotta scan. J and E. You guys don't want to tell me? Jenny and Elise. You guys had an aromatic ring. What'd you pick?
Salicylic acid.
Great. And you use this. Yeah? You find salicylic acid in your skincare ingredients? Cool. And you said that it repeats in examples for the ketone and the ester. So if you guys look at your list, the aromatic ring is there in 1-phenyl-2-propanone. The aromatic ring is there in ethyl p-aminobenzoate. The aromatic ring is also there down on the bottom right in benzyl phenyl sulfide. The aromatic ring is also there in the example for the nitro, trinitrotoluene. And then when you get into OChem 2, you're going to learn that the definition of aromatic broadens. And it's not just benzene rings, but it's rings with certain electronic properties of their electrons. But for now, great start. Good job. All right, E and N. This must be Elliot and Natalie. Great. You guys had alkyl halide. What'd you pick?
We picked thyroxine, which is like Synthroid, so it's like that's like a artificial like a hormone replacement if your body can't make like that thyroid hormone.
Wow,
So it's the same thing.
that's cool.
Yeah, and then it's repeats into the acid chloride.
Oh yes. Okay, so I might push back and say the acid chloride, bottom left, does not have an alkyl chloride because that halogen is bonded to a carbonyl carbon. So it does have very different chemical properties. In fact, there's something to be said about this actually not being an alkyl chloride, but rather being an aryl, or sorry, there's no chlorine. Not being an alkyl halide, but being an aryl halide, because it's not bonded to one of our alkyl groups, alkane, alkene, alkyne. It's bonded to one of the aromatic groups. To be honest, being bonded to an alkane has different chemical properties than being bonded to an alkene, which has different chemical properties than being bonded to an aromatic ring. But it's a good start, and I'm happy with it because a lot of people do kind of clump all of them together and just say carbon-halogen bonds, alkyl halides. So it's not well defined, and this is a great example. I like it a lot. All three of them, though, would be different from our acid chloride. So I'm glad you looked for it, but I'm just going to point out probably the least similar to them. Great work. All right, our last group, Will and Andy. What'd you pick?
So we picked dimethyl sulfide. So do you want me to say it?
You like cabbage?
So this chemical has like I was like looking at some things. It's like I knew like the properties of like cooking and like how like certain like vegetables like asparagus and cabbage had like breakdown products that led to this being given off.
Mm-hmm.
Apparently it's also like one of the main contributing factors to cloud formation in the atmosphere.
Oh, that is interesting.
So that's because of the marine cycle, so I didn't know that.
Oh.
So that's the reason why it was one of the main reasons we have clouds apparently.
So clouds form because water molecules
Yeah.
all aggregate around usually some particulate.
Yeah.
And I could see how sulfide could maybe do some strong dipole bonding with water molecules and cause them to kind of aggregate and form droplets. That's interesting. Dimethyl sulfide is a reagent we'll use in reactions this semester, and sometimes it's abbreviated as just DMS. We'll actually use it as a reducing agent, so it will take oxygen away from the reaction and become DMSO. Has anybody ever worked with DMSO? As what?
I mean, I know what it is. It's a solvent, right?
Yeah, it's a pretty common solvent. So it's interesting that we can actually use DMS as a precursor to DMSO, which is a byproduct in a reaction, but often used as a solvent. So that's great. Also, if it looks like kind of a strange structure, that's because it is. It's just two methyl groups bonded to that sulfur. So sometimes condensed structure gives more information. Sometimes bond line is what you want. It's a weird structure. All right, I want you guys to take a break, get up and move around, and I'm gonna clear the board and we're gonna move past functional groups and look more into alkanes.
Yeah, I was like, more I've seen like so many things that are talking about this. I didn't know like if you're ocean and that like leads to like how it water. It's like so weird. Yeah. No, I'll be fine. I'm not starting. I'm just trying to get like I usually eat later because I know I'm not gonna get home. But
Oh no. Nobody was going to copy those all down, right?
No, that's not real. It's all stuff.
It's our first last meeting. It's not. All right, guys, are you ready? First things first, your next analysis of an organic compound assignment is due, where you are going to analyze your structure for the functional groups that are in it. And again, this is a mastery-based assignment all semester long. So if you don't get it right the first time, I'm going to give you some feedback on it and ask you to resubmit. But you can do this as a document. So all you have to do is just go in and edit that document. You can write it out if you want to, but there's really no need for it. Take that sheet, take the knowledge you learned today, and apply it towards your molecule so that you get more practice with it. Remember, I didn't pick that molecule. You did. All right. We're moving now into a section on alkanes. It's that simplest functional group, that group that some people say is not a group. Alkanes follow a chemical formula CnH2n plus 2. Have you ever tried saying that as a sentence? 2 more than twice as many hydrogens per carbon. Whew, it's weird. But it does allow you to do some quick mental math. For instance, in my Gen Chem lecture this morning, I talked about the law of definite proportions, which has never done anything for me in chemistry, so I don't know why we teach it. Well, actually, the law of definite proportions makes sense, but the law of multiple proportions, that's a waste of time. But this is kind of the law of definite proportions. For every n number of carbons, you'll have 2 more than twice as many that number. So I gave some examples, and I needed to come up with the chemical formula of octane. And I know octane has 8 carbons, but I don't have it memorized how many hydrogens, so I just doubled it and added 2. Made it pretty easy. These only have sigma bonds. There are no pi bonds. And because of that, these are relatively inert compounds. The only reaction that we'll see them do this semester, and this is really just a preview for later. Keep in mind, I'm abbreviating reaction here, RXN. The only reaction they do is radical halogenation. So I'll give you an example. If you have methane and you react it with chlorine in the presence of light, H nu, you can get chloromethane. There's a byproduct to that reaction. Do you think you can tell me what it is? HCl. The hydrogen of methane is missing and one of the chlorines is unbalanced. And it gets a lot more complicated. Later in the semester, we're actually going to analyze this reaction, and we're going to talk about why in organic synthesis, when you're trying to take one molecule and build it into a different molecule, we don't usually use chlorine. It's so reactive, you can't control what carbon it reacts with. And so instead, we use bromine, which is more selective. And so we can control where in our molecule it reacts. But keep in mind, this is all it can do. It reacts with radical chlorine, and that radical chlorine is produced in the presence of ultraviolet light. That's really its chemical property. If we talk about its physical property, it only experiences dispersion forces. That's because alkanes, having no heteroatoms, are always nonpolar molecules. Now we said that the CH bond is called nonpolar, but it still has a dipole. It's just a weak dipole. But nevertheless, when the only thing you have in a compound is 2 atoms, the exterior of that molecule will always have the same pole, which means the exterior of the molecule never has a dipole itself. So only experiences dispersion. By the way, sometimes you'll see this abbreviated VDW. Do you remember what that's for? Van der Waals forces. I think it's German, so I think it is pronounced Van der Waals. The V as a W. A double V, really. When you type it, it's a double V. Anyways, I digress. I do want to talk about how their dispersion forces differ, though. So let's look at methane versus octane. At room temperature and pressure, these have 2 different states of matter. Which of these is a liquid? octane, because you can pump it into your car. And which of these is a gas? Methane, because you can pipe it into your house, and then you need to put some sulfur flavorings in it so that you can smell if there's a leak, because it's odorless. Octane, not so odorless. Okay, so why is it that octane is a liquid and methane is a gas if they experience the same weak force? Is it that obvious? You're smirking. What do you think?
It's bigger.
It's happy or you're happy? Oh,
It's happy.
yeah. That's why it's a liquid.
It's bigger.
Okay. Will, you want to add to it's bigger?
Is it because there's like, I'm trying to remember based off of what it was. Is it because it has a lower surface? No, that's when it's trying to remember what it was.
Well, I'm telling you that this is a liquid and this is a gas at the same temperature and pressure. What can you tell me about surface area? Comparing the two.
Wait, I'm sorry.
You weren't going to talk about surface area? I heard you say surface.
I'm trying to remember. Well, I was just trying to remember where in my head I was going with that, but I lost my train of thought.
That's okay. Kiara?
Sorry, I know there was a question about this in the previous reading quiz.
Good
about
job.
like surface area
Yeah?
and about how the heat would affect it more if it was smaller, or like temperature would,
Yeah?
and it would make it a gas.
Right. When this molecule gets put next to another molecule of octane, look at all that space that can have interaction. And when this gets put next to another molecule of methane, look at how little interaction there is between those molecules. So if dispersion forces are like weak little magnets, then the bigger your weak magnet, the stronger the magnetic attraction. And it takes energy to pull magnets apart, right? The stronger the magnets are, the more energy it takes to pull them apart. That's your room temperature. It's some amount of energy that's giving these molecules energy to move.
So it is the bigger surface area?
Absolutely.
I'm sorry, I got confused when you were saying gas versus liquid. I was like, wait, are we even talking about the same thing?
Totally.
Yeah.
At the same temperature and pressure, all of these molecules have the same amount of kinetic energy. But the kinetic energy in these molecules is not enough to get them to break free of each other. It's just enough to move past each other. But they're staying in contact. They still have some attraction. All of this attraction. Whereas my small molecule, it only has a tiny bit of attraction to the other molecules, a tiny bit of space to interact with other molecules. So that same amount of kinetic energy, it just flies by. Never even recognizes a chance to interact with the other molecule. And then let's compare this to the compound that we had up here, Vaseline, CH3, CH228, or was it 18? Oh, that's too bad. 18 CH3. What state of matter is Vaseline at room temperature and pressure? Yeah, maybe you could argue, right? Because if you tip it over, does it move and displace itself? Kind of. I don't know, actually. Maybe need to check.
Yours in your car, like it doesn't in the car, but not at room temperature.
Okay, so then its melting point is warm enough that you can get to it in the car.
Yeah.
Okay, so Vaseline, although let's see, this is 20 carbons. I actually don't know my 20 very well, so I'm just going to put Vaseline. But we could provide its name. I don't know if anybody knows the Greek for 20, like dodeca. I think that's 12. Anyways, if we draw out the bond line structure so that we can compare it to these, that's 20 lines. It just gets really long. and then you put all those molecules next to each other, and you have increased interactions. So the idea here is that with increased surface area, you have an increased boiling point and melting point. More surface area, better contact. More contact, more energy required to separate molecules from each other. More energy required to separate them from each other, more energy required to change phase. Now let's take a bit of a different example. This is a molecule called pentane. Oops, I drew hexane. This is a molecule called pentane. And this is a molecule called 2,2-dimethyl butane, propane, excuse me. Pentane, 2,2-dimethyl propane. Which of these do you think has a larger surface area? Keep in mind that this compound is C5H10, and this compound is C5H, sorry, that's 2N plus 2, C5H12. They have the same chemical formula. They're essentially the same amount of mass, but they do not have the same boiling point. They do not have the same melting point. The amount of energy required to change phase is not related to the mass of the compound. Has nothing to do with the mass of the compound, to an extent. These have the same mass. Which of them do you think has a larger surface area? Which of them do you think has a larger boiling point? Why don't you discuss in your groups quick? Just spend a minute chatting. Larger surface area, larger boiling point. All right, what'd you come to? Raise your hand if your group said pentane has more surface area, higher boiling point. And if you said 2,2-dimethyl propane. We're split, like pretty much down the middle. Can I get volunteers to share their points of view?
All right, I'll go.
Let's hear
They
it.
volunteered me again. I think, from what I remember, so pentane versus the one on the right, on dimethylpropane. Pentane is like, I don't want to say linear, but it's more, it's not, it's like, I don't remember the term. It's like it's not stacked on top of each other.
Mm.
Like it's because it's not doing like the crossover with that the dimethylpropane is doing. It has a larger surface area because it's less spherical.
So being less spherical is increasing its surface area?
Yes.
Is that what you're saying?
I'm trying to remember the wording in the book. There was like a term that I'm forgetting.
Okay. And how about somebody from the 2,2-dimethyl propane side? Willing to share your perspective? No? Stretching more. Yeah. We refer to this as branching, actually. We say that this is a linear chain and this is a branched chain. All right, well, I'm actually going to bring it back to this idea of circular. Imagine you have a basketball, which is actually what this compound kind of looks like. It's fairly spherical. All right, now stack that basketball with other basketballs. How much contact do you have with the other basketballs? A lot or a little? Just a little bit of contact between them. That's your induced dipole opportunity. It's just a small amount. Now imagine you take that basketball and you cut it open and you lay it flat. And now you stack those cut basketballs together. What is it going to look like? It's going to look like it has a lot more contact. You're increasing the opportunity for van der Waals forces. You're increasing the opportunity for induced dipole forces. You're increasing surface area. I like this idea that it feels like the branched structure is stretching out more, but because of that, it's actually putting a lot more of its structure on the inside rather than spreading it out flat. So which of these do you think has a higher boiling point? Which of these requires more energy to boil? Pentane. Higher boiling point, melting point. Cool. Now this idea of two compounds with the same chemical formula, but being different structures, is a relationship that we call structural isomerism. Isomer is a two-part word. Iso means the same, and mer means unit. Like if you have a polymer, it means that you have many units repeating. If you have an isoelectronic species, it means that two things have the same number of ions, like neon gas and fluoride ion and oxide ion, isoelectronic. So isomers are things that have the same unit. And the unit that we're talking about here is chemical formula. Structural actually gets changed sometimes for constitutional. One of them is a dictatorship and one is a republic. No. But it means they're made up different. They're connected differently. Their structure is unique. And that's what these two compounds are. They're structural isomers of each other. And we're going to be dealing a lot with structural isomers throughout the semester. One important thing in our class is actually avoiding drawing structural isomers instead of something else. So, I thought we'd get into nomenclature a little bit more today, but with the time we have left, I think I'd rather stay off of it. So I want to do more of an exercise diving into structural isomers. And I think this exercise is suited not just for alkanes, but for all kinds of structures. So structures with heteroatoms and structures with carbonyls and stuff like that. But there is one thing that makes it a little bit challenging to do structural isomers if you're not aware of it first. And that's degrees of unsaturation. You guys are going to find that degrees of unsaturation is one of the learning objectives under section 4, but section 3 and 4 really bleed together. When we do nomenclature, they're really going to bleed together too. A compound is saturated if every atom is bonded to as many other unique atoms as possible. In other words, no two atoms bond to each other more than once, and no two atoms bond to the same atom and somehow also to each other. So, unsaturation results from pi bonds and rings. That means you could have a compound with a pi bond that has a structural isomer that has a ring without a pi bond, because they would have the same chemical formula, the same degrees of unsaturation. And we can calculate degrees of unsaturation using this equation. Degrees of unsaturation. Call it the 2 chicken rule. 2 times carbon minus hydrogen minus halogens plus nitrogen plus 2 divided by 2. The 2 chicken rule starts with 2, ends with 2, divides by 2, has 2 subtractions, 2 additions, and it spells chicken. It's really easy to remember once you practice it a few times. Notice one really familiar atom that's not in the 2 chicken rule. Oxygen. Oxygen being present in a compound doesn't change or impact degrees of unsaturation. Whereas the number of hydrogens and halogens are kind of interchangeable. That's why you have to subtract both. Nitrogens typically increase the number of atoms you would expect relative to carbon, but oxygen won't have any change. So you can take any chemical formula, plug it into this, and you can figure out the degrees of unsaturation that are in your compound. But that doesn't tell you whether it's going to be a pi bond or a ring. So I'm going to put up a few. We'll work through them first, and then I'll have you go through the rest of them. C3H8. Degrees of unsaturation for C3H8. I know you guys are really working hard to get them all copied down. Okay. 2 times 3 minus 8 minus 0 plus 0 plus 2 divided by 2. That's 6 minus 8, negative 2, plus 2, 0. 0 divided by 2, 0. There are no degrees of unsaturation, no pi bonds, no rings. This is propane. Just a 3-carbon chain. That's the only version there can be. There are no structural isomers. C3H6. When you plug this in, you get 6 minus 6 plus 2 divided by 2. That's just 2 divided by 2, 1. How many ways can you fit 1 degree of unsaturation into this compound? Well, you could have 1 pi bond, or you could have a ring. That little triangle might look weird, but it's a pretty common shape in organic chemistry. A cyclopropane ring. And notice that from propane to propene, or propane to cyclopropane, all I've done is removed 2 hydrogens. I have unsaturated the molecule by removing 2 atoms and either double bonding atoms to each other or removing 2 atoms and then creating a loop, bonding two atoms that share an atom to each other. All right, in your tables, I'd like you to solve the degrees of unsaturation for these next two compounds and come up with as many structural isomers as you can. I want you to spend maybe 5 to 6 minutes on that. Oh, I screwed up on the last one. I screwed up on the bottom one. 1/2. I think it's 7. So that bottom one should be C4H7. And but see it into chicken. So oxygen will not sit here. Good. So
So the real difference is going to be the structures in that part.
if you're missing double bonds. Did you mean to have double bonds? Well, oxygen with one bond has a negative charge. But your chemical formula doesn't have a negative charge. And you say that you have 1 degree of unsaturation, but I don't see a pylon or a ring. Right? So either there's double bonds somewhere, or there's a ring somewhere. Okay. Or if you mean to have that oxygen neutral, probably an OH. You can't assume that hydrogen. Work with people, collaborate, see what you can come up with. Take their idea and modify it, change it into a new structure. That works. Absolutely. That's one. Now do another. When oxygen makes 3 bonds, it's positive charge. Oxygen will actually never make 4 bonds because it's too unstable. So just draw a line. Just have a CH3 group. Now, does it change when that CH3 group is on this position? Oh, is that structural isomer? This doesn't have a pi bond. Where did you mean from pi bonds? Yeah. Oh. But that's a good start. That works. Great start. Oh, there's not a second. There's 6 or 10. Keep going. Be creative. Try to get a ring in there. Yeah. You don't have any oxygens.
I know, that's weird.
Oh, okay. Well, this would start. Then just put an OH off again somewhere. And then does it change if you put the OH off there, or there, or there? It doesn't change if it goes that way or that way. Does it change if the oxygen is in the double bond? Does it change if you have a ring instead of a pi bond?
A lot of ways to represent it.
Yeah, like at least 10 probably. Those are good. Good start. Yeah, that's a good start too. Those are 2 great answers.
Yeah.
Now you've got 12 more.
It makes more sense. It's definitely easier to visualize.
Good.
Oh, sorry, if I do wrong.
That's 2 degrees of saturation. Because you have a ring and a pi bond.
Oh, I see.
But if you just make it an OH, now it's done. I guess.
Oh, okay.
I guess.
So it's just, okay.
Actually, at some point, it gets really big. At like 8 carbons, you have over 100 structural isomers, I think. Something like that. All right, guys, we're just about out of time. So I want to show you just how unlimited this can be. Because some of you are like, okay, I've got 1. What's the other 1? How many degrees of unsaturation for C4H8O? 1 degree of unsaturation, which can represent itself as a pi bond or a ring. How many degrees of unsaturation for C4H7N? 2, which means that you could have 2 pi bonds, 1 pi bond and 1 ring, or 2 rings. That's a lot of structural isomers. I'm going to stick with this one. I want you guys to work on them before we come in, and I think at the start of Wednesday's class, we'll use this as kind of the kickstart. Let's show how many different structural isomers we can show. So the first one I'll show is when there's a double bond between C and O on the last carbon, when there's a double bond between C and O on the last carbon, but I break up my carbon chain a little bit more. When there's a double bond between C and O on one of the internal carbons. And it doesn't matter which one I choose, they're the same structure. They're just rotated differently. And I can't actually change the carbon chain here anymore. But I could also have a double bond between 2 of my carbons with an alcohol on the far right side. I could have a double bond between 2 of my carbons with the alcohol 1 carbon in. I could have a double bond between 2 of my carbons with the alcohol here. I could have a double bond between 2 carbons with the alcohol here. Woo. Okay, almost done with this placement. I could have a double bond with my alcohol here, but I changed my carbon chain, so it's got this other group. And then I can have a double bond that is in between, and I can change the placement of my OH there. And that's all of the ways that I can include 1 pi bond, I think. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 structures, 10 structural isomers where the only thing I've changed is the placement of the pi bond. Then I can have a ring that looks like this, 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 a ring that looks like this. You're laughing, but it's true. I can have a ring that looks like this. I can have a ring that looks like this. And a ring that looks like this. Those are all your structural isomers. Have a great night. See? Not necessarily.
Okay.
Some are even more stable than others. See how many structural isomers you can come up with before Wednesday for C4H7N. I think it will be more, but I'm not 100% positive. All right? Take care, guys.